Here's a question that sounds almost too simple. What if different parts of a neural network didn't each get their own private set of weights, and instead reused the exact same numbers in many places? At first it sounds like a mere shortcut for saving space, and it is, but it turns out to be far deeper than that. This one idea powers convolutional networks, ties together the embeddings in language models, and lets certain transformers shrink to a fraction of their size. Reusing weights doesn't just make models smaller. Sometimes it actually makes them smarter. Let's see how. So what's the real difference between giving every part its own weights and sharing them? Here it is side by side. The default in most networks is that every layer and every position carries its own independent parameters. That gives each part maximum freedom to specialize, but it also means the parameter count balloons. A huge vocabulary, deep stacks of layers, and wide filters all pile up into an enormous model to store and train. Weight sharing forces different places to reuse one common set of parameters instead. The same numbers appear in many locations, so the model gets dramatically smaller, and when the reuse matches the structure of the problem, it also builds in a helpful assumption. That assumption acts like a gentle constraint that improves how the model generalizes to new data. This idea shows up in several forms across deep learning. Walk through them one at a time. In a convolutional network, one small filter slides across the entire image, reusing its weights at every position. That single act slashes the parameter count and bakes in translation invariance. A cat is a cat whether it sits in the top corner or the bottom, because the very same detector looks everywhere. In transformers, a common form ties the input embedding to the output projection. The matrix that turns tokens into vectors and the one that turns vectors back into token probabilities become a single shared set of weights, which saves a big chunk of parameters and often improves quality. Albert takes it further, reusing the very same transformer block weights across all of its layers. A model that looks a dozen layers deep carries the parameter count of just one block, which shrinks it dramatically while still stacking that same computation over and over again to build up depth. Each of these forms does the same two things at once. It cuts the parameter count sharply, and it injects structure, a built-in assumption about the problem, that can act as gentle regularization and help the model generalize better to new data. Boil it down, and three ideas carry weight sharing. It reuses the same parameters in many places. Rather than every layer or position owning its own private weights, one shared copy does the work everywhere it's needed, and that reuse is the whole mechanism. It shrinks model size and can add a useful inductive bias. When the shared structure fits the task, like translation invariance in images, the reuse doesn't just save memory, it constrains the model sensibly and improves how well it generalizes. It trades away some flexibility for those savings. Forcing layers or positions to share weights limits what each can specialize in, which can cap capacity. Albert gives up some per-layer expressiveness in exchange for its huge reduction in size. Alright, let's lock in what matters. Weight sharing means reusing the same parameters in multiple places within a model, which shrinks its size and can add a useful inductive bias. It appears throughout deep learning. Sliding filters in convolutions, tied input and output embeddings in transformers, and one block reused across all layers in Albert. When the shared structure matches the problem, it improves generalization as a form of built-in regularization, not merely saving memory. Its trade-off is reduced flexibility, since shared parts can't fully specialize, and it's a design time choice rather than post-hoc compression like pruning. If deep learning ideas made this simple appeal to you, there's a whole library of them waiting at standarity.com. Come dive in.